Good afternoon, this is Annie Schweitzer, and this is a little video on big idea number 3, changes matter. Basically, this is chemical reactions. We'll just kind of preview a few of the things here that you want to be aware of, refresh your memory as far as chemical reactions are concerned. The first part here is just kind of talking about maybe balancing chemical reactions involving stoichiometric ratios, relationships between products and reactants. Then we have the basic different types of chemical reactions. We'll highlight each individual type in this PowerPoint. And then we have the energy associated with these types of reactions. That also might be included in thermodynamics. Alright, so types of chemical reactions. They're going to give you synthesis, decomposition. These I usually don't classify in this sense. I usually just classify them as these guys below. But technically a synthesis reaction could be a few different types of reactions, but in reality it's just two things coming together. Let's say H2 plus O2 yields H2O. This would be a classic synthesis reaction. But it's also a redox reaction, where this thing is changing from a zero charge and a zero charge to a +1 and a -2. I could have, let's say, a lithium plus Cl. Well, I guess it depends how soluble it is, but if this thing forms lithium chloride, then this is what I refer to as a solubility reaction. So there's a few different types of reactions. So we have solubility, acid-base, and then oxidation reduction. A little bit about solubility. One of my main phrases in honors chemistry is different combinations of different ions have different solubilities. So a few things we might want to note about an example here. One, mixing two solutions together of 0.5 molar NaCl plus 0.5 molar lead nitrate will produce an ionic solid. In today's day of the new curriculum of AP chemistry, they likely would even give you the precipitate, but I think a student should be able to identify the solid being produced, write a molecular ionic and a net ionic equation. The identity of the solid, right? So inside this beaker, and we'll maybe draw a picture of it here. Well, let's just go with this first. Due to the high solubility of the sodium ions and the nitrate ions, lead chloride will be the precipitate, and these will be the spectators. I'm going to refer to as spectator ions. Alright, so we're at the equations. We got lead nitrate, sodium chloride yields sodium nitrate. These all would be labeled as aqueous. And then we have, of course, our solid here. So if you want to be a little more detail oriented, you can put those aqueuses on those two guys as well. An ionic equation isn't as useful or isn't as much asked about in different types of questions, but I will say though that when I am drawing a picture, if I'm drawing a picture of a beaker of this type of reaction, I would generally use the ionic equation to draw the picture. Whether I do two beakers, one before, and then we could have another beaker, what it looks like after the reaction's done. Very often I use this reaction. A net ionic equation removes spectators. This is a pretty common type situation. Alright, so let's draw these pictures before and after. So we have the lead nitrate. Again, we have Pb2 plus, and we have the nitrate. And of course, it's going to come in a 2-to-1 ratio. We have Na plus, and I have Cl minus. Now again, one thing you kind of want to be aware of as well is the size of the particles when you're drawing them, or if you are looking at picking a picture out, make sure that you take a look at the size of the particular items that are involved there. So let's go with this guy being maybe a little bit smaller, and then we have a little bigger version of the chloride. And then together we form our solid, which would be PbCl2. And then we'd have a spectator would be Na plus and Cl minus. Now, keep in mind, the way I've drawn this at this point would be something that would involve exactly the right amounts of these. Now, this thing reacts in a, if I balance this thing, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 2 chlorides, 2 chlorides. Okay, so it's balanced. So if I have equal concentrations of these things, let's say I think it was 0.5 molar, 0.5 molar, then I would require, let's say, 20 milliliters of this guy and 10 milliliters of this guy to get this picture that I have down below here. But let's say one of these reactants goes in excess. Let's say I bump this guy from 10 up to 20. So now this is an excess, and this is the limiting reactant. Okay, so how does my picture change? Well, the chlorine, and I drew this picture incorrectly before. This original would be a NO3 minus. And I would have another. These represent the right proportions. Let's put 2 of them in here to represent the one time through the chemical equation. Okay, so 2 sodiums, 2 nitrates. Okay, so let's make the lead nitrate in excess. That means I have to add more lead and more nitrate. So I have another Pb2 plus, and I have 2 more nitrates. Hard to see that. There we go. So again, now I have an excess and limiting reactant. Keep in mind there are really 3 species that are in here. I have each of my excess, my spectator ions, which would be the sodium. Okay, you can even go back to this guy. Would be my sodiums in there, sodium, and then I have my nitrates in there, and then now I have my excess reactant, which is going to be the lead, and a little bit more nitrate. One last thing I'd mention about this: in any time you're drawing a picture, make sure your positives equal your negatives. Very important. And that's just a repeat of the previous slide. Alright, so acid-base reactions. We have hydrolysis. Might be the most important acid-base reaction, might just be hydrolysis. This is the basis by which we write our Ka and Kb expressions. Ka equals, in this case, concentration of H3O plus, concentration of X negative, concentration of HX. And then the same thing for the Kb. Alright, strong acids versus weak acids. Okay, acids. Keep in mind there are 6 strong acids, so if you come across an acid that's not on that list, it is going to be weak. And it's very important that you understand you can do the pH of a strong acid. It goes to completion. Every reaction either goes to equilibrium or it goes to completion. Now, in this case, I have a 0.1 molar HCl solution. As I run a completion, the 0.1 molar ends up being the same as this value. So quite often for strong acids, we realize we can just plug the concentration straight into the negative log equation. Negative log of 0.1 equals 1. Don't forget that since we're measuring H plus ions, that this is in fact a pH, and if we were doing a base equation, it would give me the POH. Let's draw a picture of this thing. So let's do the before picture. Granted, as soon as HCl enters water, it hydrolyzes 2 of the products. But so drawing this thing here could be something as simple as just plain HCl. Not as common to draw this picture out like this because it just doesn't really exist like this. It would be better if it was, let's say, HF. That would be a weak acid. Then many of those do in fact stay together. But give it just a few split seconds, and this thing will convert to products. Would it be H plus and Cl minus, H plus and Cl minus. Now keep in mind, if I were to draw this thing even a little better yet, we'd want our H plus to be much smaller, because in fact it is, and the chloride's much bigger. Either way, you also could draw this thing as H3O plus if you'd like. Alright, determine the pH of a weak acid. If we have a 0.1 molar HX, remember we need a Ka for this thing and a concentration. So I just sort of made up a Ka for this guy. In this case, the Ka is 1.5 e to the negative 7th. So if this is my weak acid, this is my conjugate base right here. So this thing is a weak base. And of course the Ka of this guy times the Kb of that guy equals Kw, which is 1.0 e to the negative 14th. You should be aware that the strength of the K teeter-totters on 1.0 e to the negative 7th. So in this case, my acid HX is slightly stronger than my base is conjugate, than the conjugate bases. So if by chance we had a reaction here where we had HX plus H2O yields H3O plus X negative initial concentrations, I have a certain concentration of acid, a certain concentration of base. And if these two guys were equal, I would still be acidic because my Ka is stronger, my acid is stronger than my base. But either way, in this case, for determining the pH of a weak acid, it's critically important that you be able to do an ice table, initial stoichiometric ratio, and I have a couple of variables here. Minus X, water will not play a role. 0 plus X, and then X and X, and of course this is the initial amount minus X. So a few boxes here of things that we generally try to find. Normally we would also, if given the initial concentration, be looking for the H3O plus ion concentration. Also keep in mind, if I ever want to find a K value for this thing, Ka or Kb, anytime I want on a K, everything from the equilibrium line just gets plugged into the equilibrium expression, and I wrote that above before, but for this guy it would be Ka equals the concentration of H3O plus, concentration of X negative, concentration of HX. So all of these guys get plugged into here and solve for a K. So if they ever want a K value, you know you need all the concentrations at equilibrium. Alright, so I'm just going to draw the ending picture of this thing. It would be HX, and we have HX, water line, HX, HX. So the more of these I draw, the more it's going to be concentrated. Dilute would be just having less of them. And then, of course, because it's a weak acid, I have one or two of them, a small percentage that would be ionized. Don't forget that we do have the percent ionize. Is another way they describe an acid. In this case, it would be the amount that changes divided by the original times 100. So that is another one that is fairly common to describe an acid. So how much change would be your stoichiometric ratio, your X value, and how much the original you had is going to be this guy right here, the original concentration. Neutralization reactions. This is something that is used probably maybe even exclusively or just about exclusively to titrations. We are titrating weak acid with an unknown base or vice versa. Usually it's a strong versus a weak, two strongs, strong versus a strong. But keep in mind that a weak acid, its conjugate is a weak base. A strong acid, its conjugate is neutral. A strong base, this conjugate is neutral as well. So in this case, this guy's conjugate is going to the sodium. This guy's conjugate is going to the fluoride. This is a strong base, so this guy is neutral. This guy is a weak acid, and therefore this guy is a weak base. This salt, therefore, is a weak base. The question here says, what's the pH at the equivalency point? On a chart that would look like, in this case, maybe like this. And of course right here, this would be just above the 7 mark, so at the equivalency point, all we have left is this salt. Everything else is gone, so it's going to be basic at this point. And if you're, you should be able to calculate the pH at this very point, and that's an important process. Of course, we need to be given the initial concentrations, different things, but that's an important question you should be able to answer. Oxidation reduction reactions. First, you must be able to recognize a redox reaction when you see one. Assign oxidation states, check reactants and products to see if charges are changing. If they change, you should be able to determine who's being oxidized, who's being reduced. Here's an example. We have carbon monoxide is most commonly produced from incomplete combustion. So in this case, if we have carbon monoxide, it can actually be burned again by oxygen to produce carbon dioxide. In this case, could balance it, but we have a -2 and a +2, 0, and then a -2 and a +4. Those are the oxidation states, so who's being oxidized, who's being reduced. In this case, you'll see that the oxygen is going from a 0 to a -2, so it's gaining electrons, therefore it's reduced. The carbon is going from a +2 to a +4, so it's being oxidized. Alright, simple redox is one that I generally, my name for your basic simple type of redox reaction. Someone in regular chemistry might call this thing a single replacement. Things you should be able to do, you should be able to write out the reaction, balance using half fractions, determine the voltage, determine if it's spontaneous or not based on that voltage, who's being oxidized, who's being reduced, all things you should be able to do. And here are all the answers to those questions, all the different types of chemical ways to represent that equation. The half reactions, it's voltage because it's positive. It is going to run, which all it means is it's going to proceed to products all by its lonesome without having to invest any energy or any work into it. Don't forget to flip the sign on this guy here. This is the oxidation version, so it was reversed on the reduction potential chart. Here's your typical galvanic cell. All sorts of pieces in here. The cathode label, the anode label. Remember, electric current or electric electrons flow from the anode to the cathode. So we have the little electrons here. As you produce our loop all the way around, the negatives will take this path. So this will be the negative path. So notice they point out here that the sulfates are moving this direction. That's because they're negative. Conversely, positives could go this way to also keep the charge balanced. Here's a few questions that you should be able to answer. The masses of the posts, the concentrations, what's happening inside this cell, and whatnot. Electrolytic reactions, of course, reversing the process using electricity to produce chemistry. The most common question would be to figure out how much gas is being produced with a certain amperage over time. There's a little example here coming up of that. Here's another picture of it. I like this picture specifically. It shows even the spectator ions, hydroxides. Everything negative is going towards this particular positive electrode, and then electrons flow in this direction. So electrons flow from the anode to the cathode. That's very important. In this case, chlorine is being produced here, chlorine gas. So my question is this: if a reaction runs for 2 amps, 15 minutes, how much volume of chlorine gas will be produced at STP? All right, and here's the math on this, and I'll let you just take a look at this if you'd like. Some typical questions we have here. All right, so this is referring to an acid-base reaction, and keep in mind that this is the acid conjugate base. Acid conjugate base. This one here is a little unique. The water is being produced both into an acid and a conjugate base, so kind of an odd situation there. But the question asks, which of the following is a conjugate acid-base pair? Not too concerned about the fact that it's Bronsted-Lowry, but notice the first one's got this guy, and the second one here is located here, so they're not in the same reaction. I'm literally looking for one and the other in the same reaction, and that is going to be letter B. So this guy and this guy is this. Be this guy and this guy. They are acid-base conjugate pairs. Keep in mind that another term that comes up here is this guy is diprotic. So 15 here we covered in a previous chapter. Alright, so we got this particular question. Student mixes dilute silver nitrate with excess sodium chloride to form silver chloride, and as represented by net ion equation above, which the following diagrams below represents the ions that are present in significant concentrations. So I could just write this out here for a moment. We got Ag plus, we have NO3 minus, plus we have Cl minus, plus we have Ag plus. So those are all of our potential beginnings, and in fact it was excess sodium chloride, so I'm going to put this down here as being Na plus, and this is going to produce AgCl plus Na plus NO3 minus. So what should be there in the end? Well, we're going to have our spectators. This will be on the bottom. All of them have it on the bottom. We have Na plus, we have NO3 minus, and we have an excess sodium chloride. So I also would expect the sodium and the chloride to be present. No silver. The nitrate is drawn already over here. So the only thing I wouldn't get would be silver plus ions. So this guy is out right there. We got these guys are out. And therefore, what is left here? We got sodiums here. I got chlorides. Okay, this guy doesn't have any chlorides. So this is my answer right here. Alright, and of course C is the correct answer for that guy. And let's move on. Alright, so this is a reaction that says, well, okay, we have 1 atmosphere of this reaction. This is starting out 1 atmosphere. If the reaction were to go to completion, what would be the total pressure inside the container? Alright, well, in this case, because we have 1 mole going to 2 moles, 2 particles, then it's going to double. We're going to double in our particles, and simply by even with the word just pivnerd, then the number of particles will double, and therefore the pressure will double for a given temperature and volume. So the answer is 2 atmospheres. Alright. Next one here. It says, okay, elements potassium and chlorine are directed into a compound of potassium chloride according to the equation above. Refer to the information above the table to answer the question. Okay, so in this sense, we have what remains in the reaction vessel after equal masses of potassium and chlorine have reacted until either one or both the reactants has completely consumed. So we know we're going to get KCl in this reaction. So we immediately can, well, every single one of them has KCl in it. So I want to know what my limiting reactant is going to be. I would say this one might be out just because they have both things present, unless we're going to equilibrium. That's not going to be the case. So how do we solve this problem? Well, it says we have equal masses. So in my mind, I sketch out that we have 40 grams because that's going to give me approximately close to 1 mole. And that being said, 40 grams of the other guy is a little bit more than a half. So at 70 grams per mole, again, there's no calculator on this test, so we got to estimate, which gives me a little more than half. And since it's not used up, this isn't used up twice as fast, we have a little bit extra of this guy left over. I'm only going to need about 0.5. If I use up all of this guy, I'm only going to need, okay, 0.5 moles of the in this case the chlorine. So the chlorine will be in excess, and therefore this guy will be left over. Next up here, we have all these different questions surrounding around this particular item. Now again, they're running off of some galvanic cells. There's different types of metals in each of this cell. Cell 1, cell 2, cell 1, cell 3, cell 2, cell 3. So 2 and 3 are comprised of all of the pieces and stuff. So first things first, what is the standard cell potential in cell Z? Now, here's that question here. Now this one here is might be a little tough to see at first, but if you look at it, you'll see that these two guys together kind of look like they might add up to the overall of this guy. And that is what happens here. If you leave X the way it is, this guy the way it is, but if you were to flip this guy around, then the aluminums would cancel. Again, I had to flip it. I didn't rewrite this thing. And then the Fe2 pluses would cancel. Fe still would stay the way it is. What else would cancel? The aluminum solid would cancel. So all the aluminum stuff would cancel, and I would get this reaction. And when I flip a reaction, the cell potential flips, and then you simply add them together. Here's my addition or subtraction. I get a 0.78 volts. All right. Now it says if galvanic cells X or Y and Z, which cell is in the which takes place in the cell 3. All right. So in this case, they tell you what is going on here. They tell you, okay, strip 3 has iron in it. So it says in galvanic cells Y and Z, which of the following takes place in cell 3? So they want to know, okay, cell 3 is the iron. So the iron is going from a +2 Fe +2 going to Fe solid. Now this is in the Y cell. So adding 2 electrons to this side, this is reduction. And then the other guy, I have Fe solid going to Fe2 plus 2 electrons. So this guy is oxidation. This is the Z cell. So in the Y cell, I have oxidation or reduction, and in the Z cell, I have oxidation. And that would be matching up with letter C. What else we got here? It says in the half cell containing 1 mole per liter of iron nitrate in galvanic cells, is in Y and Z is replaced with 5 molar. So we're upping the concentration of the iron 2 plus from a 1 molar solution to a 5 molar solution. And again, we're increasing the concentration. That depends if you're increasing the concentration of a reactant or increasing the concentration of a product. Increasing the concentration of a reactant is going to cause your voltage to increase. Increasing the concentration of a product causes your voltage to go down. And if you notice in the Y equation, the Fe2 plus is a reactant, so this will cause the voltage to go up. And in the Z, it is a product which causes the voltage to go down. All right, so that would be, I think, what, letter C. Okay. And that comes to the end of our questions. This is big idea number 3. Thank you very much.